Hello students, welcome back. I hope you have watched my previous videos on inductive effect. Now, in these next videos, we will cover resonance effect or mesomeric effect and the other effects pertain to electron displacement effects. Okay, so before we exactly know what is resonance effect and mesomeric effect, see, many teachers will tell you resonance effect and mesomeric effect are the same. No, they are not same. They are slightly different. It is due to resonance, mesomeric effect comes into picture. Okay, due to resonance, mesomeric effect comes into picture. Okay, so in order to understand mesomeric effect, first we should know the resonance effect. Okay, I repeat, in order to know mesomeric effect, we should understand resonance effect. Okay, by the way, what is resonance and why did the concept of resonance arise? Guys, look at here, certain organic molecules, we can represent certain organic molecules in two different structures, in one or more structures, not just two. Okay, certain organic molecules can be represented in one or more structures. Okay, for example, well-known example, benzene. Okay, see this, I can represent benzene like this. I can write the structure of benzene like this, or else I can write the structure of benzene like this, isn't it? Okay, correct? Yes or no? If I call this as first carbon, second carbon, third carbon, fourth carbon, fifth and sixth carbon, again first carbon, second carbon, third carbon, fourth carbon, fifth carbon and sixth carbon. I hope you can see the difference between this structure and this structure. What is the difference between this and this structure? Here there is double bond between first and second carbon, double bond between third and fourth carbon, double bond between fifth and sixth carbon. Whereas in this structure, okay, there is double bond between second and third carbon, fourth and fifth carbon and first and sixth carbon. Okay, there is just shift of the pi electrons. There is just the shift of the double bond between this structure and this structure. So like this, we can have so many other molecules wherein their structures can be represented in one or more different way. One more example if I can consider, okay, for example, carbonate. Okay, we know the molecular formula of carbonate, CO3 2-, isn't it? Okay, I can write the structure of carbonate in many forms. For example, okay, see, this is one form of carbonate. Okay, yes, this is another form. Look at here. Okay, and this is another form. Okay, look at here. I can represent carbonate in three different ways. I can write or I can draw the structures of carbonate in three different forms. Isn't it? Am I correct? Okay, yes, why did this happen? What exactly is resonance? Look at here, these two are the different structures of benzene, but they are not the actual structure of benzene. Okay, again, these are the different structures of carbonate, but these three are not the actual structures of carbonate. See, these structures are called as resonating structures. Resonating structures. What are they called as? Resonating structures. What are these three called as? Yes, these three are also called as resonating structures. Okay, resonating structures. Then let us understand what exactly is resonance. I hope you understood. I hope it is clear. Okay, certain organic molecules, the structures of certain organic molecules can be written in one or more different forms. Those different forms are called as resonating structures. These two, benzene can be represented in any one of these ways. Okay, so these two different forms, okay, they are known as resonating structures. Whereas carbonate, the structure of carbonate, okay, yes, can be written either this way or this or this. Okay, these three are called as resonating structures of carbonate. Carbonate, understood? So then what is resonance here? What is resonance? Okay, look at here. I'll take three examples. Okay, I will take three examples. First example, let me consider this molecule. CH2, double bond, CH, okay, yes, single bond, CH2 plus. Yes, I have this molecule. Okay, yes. Now you can observe here there is double bond, single bond and a positive charge. Okay, we know, okay, I have told you in my previous videos also, if there is a double bond, one of them is going to be a sigma bond, the other one is going to be a pi bond. Okay, sigma bond is a strong bond, pi bond is a weak bond. Okay, since pi bond involves, okay, the overlapping of the atomic orbital sideways, the extent of overlapping will be weak in case of pi bond, hence pi bond is a weak bond. Okay, the pi electrons are loosely held, okay, between the shared pair of atoms. Please note this point. Sigma bond will be a strong bond, pi bond is going to be a weak bond, and the pi electrons, what does sigma bond consist of? Sigma electrons. And what does pi bond consist of? Pi electrons. The pi electrons will be loosely held between the two atoms, whereas sigma bond, since it is a strong bond, the sigma electrons will be tightly held between the two atoms, So I can say sigma bond consists of sigma electrons, pi bond consists of pi electrons, and pi electrons are, okay, loosely held, okay, between the two atoms. I hope it is clear. So now, since pi electrons are loosely held, okay, see, these pi electrons will shift here. Okay, when these pi electrons shifts here, okay, what is going to happen? The pi electrons will be displaced between these two carbon atoms. Initially, the pi electrons were between these two carbon atoms. Okay, now these pi electrons are displaced between these two carbon atoms. Okay, what is going to happen? Okay, CH2, okay, a double bond becomes single bond, then CH. Since, okay, pi bond or the pi electrons are displaced between these two carbon atoms, now these two carbon atoms is going to get a double bond. Now just check the valency of the carbon atoms here. Okay, so this carbon 2, 3, 4. Is the valency of carbon satisfied here? Yes, we know carbon, valency of carbon is 4. Okay, carbon 2, 3, 4 satisfied. How about this carbon? Okay, carbon 1, 2, 3, 4. The valency of this carbon is also satisfied. But look at this carbon. Okay, 1, 2, 3. Okay, so the valency of this carbon is just 3. Okay, it has got one more valency. Since it's, okay, all the 4 valencies are not satisfied. Since its valency is not satisfied, this is going to get positive charge here. Okay, this will get positive charge. Are we clear? Any doubts? Okay, look at here. What is happening? Okay, the pi electrons, since the pi electrons are loosely held, they're being displaced from one carbon to another carbon. Okay, are you able to understand my point? Now I'm going to consider one more example. See this example. What is that? Okay, let me consider carbonate. As I said, C double bond O, O minus, O minus. Look at here. Let me call this as first oxygen, second oxygen and third oxygen. Okay, now what is going to happen? Okay, yes, there is pi bond. Okay, pi bond, pi electrons loosely held again. Okay, yes, pi bond is there, pi bond, sigma bond, okay, or else a double bond, single bond and negative charge. A double bond, a single bond and a negative charge. Now what is this? What is going to happen in this case is, this negative charge will be displaced here. Okay, yes, and the pi electrons will be shifted to this oxygen. Okay, the negative charge will be displaced here and the pi electrons will be shifted onto the oxygen. As a result, what will happen? Okay, yes, C O. Okay, a double bond becomes a single bond. Since the pi electrons are shifted on this oxygen is going to get a negative charge. Okay, this remains as such. Okay, since the negative charge has been displaced here, okay, this single bond becomes a double bond. I hope it's clear. This is one structure of carbonate, this is another structure of carbonate. Okay, is this final? No, this doesn't stop here. What will happen? Okay, now the negative charge from the third oxygen atom will be displaced here, and the pi electrons will be displaced on this oxygen atom. So that means we can write one more structure of carbonate. What is that? Okay, CO minus. Okay, since the negative charge is displaced here, okay, this single bond becomes double bond. Okay, and since the pi electrons are displaced onto oxygen is going to get negative charge, and this double bond becomes single bond. What are all these three? These three are, okay, the resonating structures of carbonate. And what are these two? These are the resonating structures of this molecule, isn't it? Okay, yes, is that correct? Yeah. Next, okay, what next? Let me write the resonating structures of, okay, yes, simple, benzene again. Yes, what is the other resonating structure? Okay, yes, this is the resonating structure of benzene, isn't it? Yeah, okay. Yes, are we clear? Here the pi electrons is between first and second carbon. Okay, yes, third and fourth carbon, correct? Yes, and fifth and sixth carbon. Whereas here, okay, the pi bonds, okay, that is the double bond, is between second and third carbon. Yes, okay, fourth and fifth carbon, sixth and first carbon. So what is that you are observing in all these three cases? Yes, in all these three cases, there is displacement of pi electrons, isn't it? The pi electrons are being displaced from this region to this region. Okay, here also there is displacement of pi electrons. The pi electrons are displaced towards oxygen. The pi electrons are displaced towards oxygen. The pi electrons are displaced towards oxygen, isn't it? Here also, the pi electrons, there is displacement of pi electrons. Now, in this case, okay, in case of benzene, the pi electrons are displaced from first carbon to second carbon, and here the pi electrons are between second and the third carbon. So there is displacement of pi electrons from here to here, okay, here to here, isn't it? There is displacement of pi electrons in all this case. So this is what? The displacement of pi electrons or movement of pi electrons or the shifting of pi electrons is what I call, or what we call, resonance. Understood? What is resonance? Resonance means, okay, the displacement or the shifting of or the movement of pi electrons within the molecule. The pi electrons are not moving away from the molecule. Pi electrons are not being displaced away from the molecule, isn't it? Okay, the pi electrons are displaced within the molecule. Look at here. Yes, the pi electrons are displaced from this region to this region in the same molecule, isn't it? Here the pi electrons are displaced from here to here within the same molecule. The pi electrons are displaced from here to here within the same molecule, isn't it? Okay, here the pi electrons are displaced from second carbon to third carbon. Okay, isn't it? There is shifting of pi electrons or displacement of pi electrons or movement of pi electrons, or else I can say delocalization of pi electrons within the molecule is called as, what is this called as? Resonance. Okay, within the molecule is known as resonance. I hope you understood. Okay, so are we clear with all this? The delocalization of pi electrons within the molecule is called as resonance. And what are these called as? These are called as, okay, these are called as resonating structures. Okay, what are these called as? Resonating structures of carbonate. Resonating structures, okay, structures of carbonate. What are these called as? These are called as resonating structures of benzene. Resonating structures of benzene. Understood? Okay, yes, this is called as allyl carbocation. So I will say that this is the no, you'll come to know what is allyl later, okay, in our further discussions. This is called as allyl carbocation. So this is the resonating structure of allyl carbocations. These are the resonating structures of carbonate, and these are the resonating structures of what? Benzene. If I consider one more example, look at here. I'll take up this. What is this? CH2 double bond CH single bond CH2 minus. Got it? Now there is a double bond, single bond and a negative charge. Double bond, single bond and a negative charge. Okay. Now what will happen? This negative charge will be displaced here. Okay, and the pi electrons will be shifted to this carbon. Okay, negative charge will be shifted to the here, and the pi electrons will be shifted to this carbon. So what is going to happen? Yes, now since the pi electrons are shifted to this carbon is going to get, this carbon will get negative charge. Double bond becomes single bond CH. Since the negative charge is displaced here, single bond becomes double bond CH2. This is called as allyl carbanion, okay, or allyl carboanion. Understood? Okay. What are these two? These two are the resonating structures. Okay. What is happening here? Here also there is delocalization of pi electrons, displacement of pi electrons, shifting of pi electrons, movement of pi electrons within the molecule. And what is this process, or what is this phenomena called as? This is called as resonance. I hope you understood. Any doubts? Yeah. And what are all this called as? These are all called the resonating structures. Trust me, no resonating structure will explain all the properties of that compound. Please. Okay, that means, did you understand my point? Please note my point. No resonating structures will explain all the properties of that particular molecule or a particular species. Okay, see, this resonating structure cannot explain all the properties of allyl carbocation, and also, okay, this resonating structure, okay, cannot explain all the properties of this allyl carbocation. So neither of these resonating structures can explain the properties of that particular molecule or that particular species. Okay, that means all these resonating structures are imaginary. They are imaginary. Okay, they are not real. They are just present on the board. They are just present on the paper. They are not real. No resonating structures are real. They are all purely imaginary. And the resonating structures cannot explain the property of any molecule. Okay, it cannot explain the properties of that molecule. See, either this resonating structure or this resonating structure cannot explain all the properties of benzene. Okay, yes, either this resonating structure or this resonating structure cannot explain all the properties of this allyl carbanion. Okay, I hope you understood. Yes, that means to say resonating structures cannot explain the properties of a particular species or particular molecule or that particular ion. Resonating structures are just imaginary. They are present only on paper or they are present only on board. Okay, they do not exist. The concept of resonating structure is purely imaginary. Any doubts? So let me write some of the properties of resonance here. Okay, please write. Okay, please note down these properties. Yes, please write down the properties or characteristics of resonance. Basically, first of all, okay, what is resonance? So what is resonance? Yes, it is nothing but, okay, the displacement, okay, or yes, delocalization or shifting or movement movement of which electrons? Which electrons, guys? Pi electrons, okay, within the molecule, isn't it? That means to say resonance is an intramolecular phenomena. Intramolecular phenomena means, what do you mean by intra and inter? If the phenomena takes place between two different molecules, then it is inter. If the phenomena takes place within the molecule, then it is called as intra. Okay, so basically resonance is an intramolecular phenomena. Okay, and here, okay, the concept of resonance is hypothetical. It is assumption. Hypothetical means it is being assumed. Yeah, this might happen. Okay, but nobody is going to guarantee that yes, this is happening. Okay, so it is purely hypothetical in nature. And all the resonating structures, yes, okay, are what? Resonating structures are imaginary. They are not real. They exist on what? Paper, or they exist on board. Any doubts? So these are basically the few characteristic properties of resonance. Okay, I hope you understood. Okay, so now I am telling you that resonating structures are not the real structures. None of the resonating structures can explain all the properties of a particular molecule, isn't it? Then how to explain the property of the molecule? Okay, that means there is no real structure of benzene at all. Okay, see, if I consider benzene, look at here. I told you that benzene exists. I can write benzene in two different ways, isn't it? This is one way, okay, of representing benzene, and this is another way of representing benzene, correct? Okay, and I told you that these two are resonating structures, isn't it? These two are resonating structures, okay, correct? But these two are resonating structures. They are not real, they are imaginary, and either this resonating structure or this resonating structure cannot explain the properties of benzene, isn't it? See, look at here. Okay, according to these two structures, there are three, okay, carbon-carbon double bond, isn't it? Carbon, okay, one, that is carbon-carbon double bond here, carbon-carbon double bond, carbon-carbon double bond. There are there are three carbon-carbon double bonds and three carbon-carbon single bonds, isn't it? So if what is the bond length between carbon and carbon if there is a double bond? Okay, carbon-carbon double bond will be of, okay, how much? 134 picometer, and carbon-carbon single bond will be of 154 picometer. That means this bond, this double bond, okay, the bond between the first and the second carbon, okay, and then third and the fourth carbon, okay, then fifth and the sixth carbon would have been of how much length? It would have been of 134 picometer, whereas the bond length between first and sixth carbon, fourth and fifth carbon, and second and third carbon, which are single bonds, okay, the bond length here would have been how much? 154 picometer. Is that correct? So this bond length would have been 134 picometer, and this bond length would have been how much? 154 picometer. Here also same, carbon-carbon double bond, this bond would have become 134 picometer, and this bond would have become 154 picometer. That means, okay, in benzene we would have expected two types of bonds. one double bond and the other single bond. Okay, if there was double bond, if there was both double bond and single bond in benzene, then we would have got two different bond lengths in benzene, isn't it? Three bond lengths of 134 picometer and three bond lengths of 154 picometer, correct? There are three, okay, yes, in these two resonating structures there are three carbon-carbon double bonds, hence we would have expected a bond length of how much? 134 picometer, and in these two resonating structures there are three carbon-carbon single bonds, isn't it? Three carbon-carbon single bonds, okay, and therefore we would have expected the three bond lengths to be of 154 picometer, 154 picometer, but actually, okay, yes, in real we don't have, okay, in real we don't have either 134 picometer or 154 picometer bond length in benzene. No, we don't have two different bond lengths in benzene. Okay, in real we have, okay, experimentally verified that in benzene all the bond lengths are same. All the bond lengths are same. If we have written the resonating structures, then we would have got two different bonds, isn't it? Three carbon-carbon double bonds and three carbon-carbon single bonds. But in real, it has been experimentally proved, okay, by X-ray diffraction or spectroscopy, etc., etc. By different techniques, we have proved that, we have concluded that all the bond lengths, all the 6 bond lengths, okay, all the bond lengths in benzene are same, I hope you understood my point. All the bond lengths in benzene are same. That means either this resin, if I consider this as the correct structure, we would have got two different bond lengths. If I had considered this as the correct structure, again we would have got two different bond lengths. No, okay, actually in benzene all the, okay, bond lengths are of, all the bonds are of equal length. Okay, that means either this is correct or this is correct. Then what is the correct structure of benzene? The correct structure of benzene is the combination of these two structures. The correct structure of benzene is the combination of these two structures. Please note this point. Okay, I am writing the correct structure of benzene. The correct structure of benzene, the exact structure of benzene is written like this. I hope you know. I hope you know this. Okay, this is the correct structure of benzene, and this correct structure, this real structure, is a combination of these two resonating structures. Okay, well, this structure is called as resonance hybrid. This is called as resonance hybrid. Understood? What is this called as? Resonance hybrid. And you should know that resonance hybrid is the real structure, okay, and this is going to be the most stable structure. Okay, this will be the most stable structure. I hope it is clear now. Okay, so now these two are the resonating structures. These resonating structures are imaginary. Okay, they will not explain the structures of, okay, any molecule or any species, okay, exact properties of any molecule or any species. So now therefore we have to write a correct structure. The correct or the proper or the real structure is the combination of all these resonating structures. And what is that correct structure called as? That is called as resonance hybrid. The resonance hybrid will be the real structure, and the resonance hybrid will be the most stable structure. Most stable structure. Okay, now let us again go back for allyl carbocation, allyl carbanion, and the structure of carbonate. Okay, see, I hope you remember in the very beginning I wrote this CH2 double bond CH single bond CH2 plus. What is the name of this species? This is called as allyl carbocation. Don't worry, I'll teach you what is allyl carbocation in the subsequent, okay, videos. Understood? Now, how did we write the resonance? The pi electrons will be shifted here, isn't it? Okay, so therefore, and the positive charge will be shifted here, correct? So now I'm going to write CH2, okay, single bond CH double bond CH2. Is that correct? So now this carbon is going to get positive charge. Now what are these two? These two are the resonating structures. Resonating structures. Okay, yes, if you can recall, resonating structures are imaginary. Okay, yes, they are not the actual structures, they are not the real structures. That means the real structure of allyl carbocation the real structure of allyl carbocation is a combination of these two structures, and I'm going to write the real structure like this. Look at here, CH2, okay, yes, CH, okay, CH2, isn't it? Observe here, one time there is, okay, if I call, okay, this as first carbon or second carbon or third carbon, look at here, in one case there is double bond between second and third carbon, and in the other case there is single bond between, okay, second and third carbon. Double bond between second and third carbon, and in the other resonating structure there is single bond between the second and third carbon. Therefore, okay, therefore the real structure contains bond which is in between double bond and single bond, which is in between double bond and single bond, isn't it? Here there is double bond, here there is single bond, but these two are not the actual structure. The actual structure contains the bond which is in between single and double bond. I will write it as partial double bond, like this, like this. I hope it is clear. Now observe first carbon and second carbon. In one resonating structure there is single bond, and in the other resonating structure there is double bond. Therefore, the bond in the actual or the real structure is somewhere in between single and double bond. Okay, what do you call that as? We call it as partial double bond. Partial double bond. So now this is going to be the real structure of allyl carbocation. And one more thing, okay, in one resonating structure this carbon has positive charge, and in the other resonating structure this carbon has the resonating structure. Therefore, the actual, in one case, okay, this resonating structure has positive charge on first carbon, and in the other case this resonating structure has, okay, positive charge on the third carbon, isn't it? Therefore, the actual structure, okay, will have partial positive charge on this carbon and partial positive charge on this carbon. Partial positive charge on this carbon and partial positive charge on this carbon. Any doubts? Okay, one more. Let me quote one more example. Okay, what is this? Okay, let us take allyl carbanion, CH2 double bond, CH single bond, CH2 minus. Now, okay, what will happen here? Okay, the negative charge will be displaced here, and the pi electrons will be displaced onto this carbon, isn't it? Therefore, this carbon is going to get negative charge, then single bond CH, double bond CH2, isn't it? Okay, so what are these two? These two are the resonating structures of allyl carbanion. This is called as allyl carbanion. Allyl carbanion. Okay, so now observe the resonating structures. Okay, once again, these two are not the real structures, they are imaginary structure. What about the real structure? What is the actual structure? Okay, let us write the actual structure. How to write the actual structure? First, write 3 carbon atoms with single bond. Now observe the resonating structures. Let me call this as first carbon, second carbon and third carbon. In this first resonating structure, there is double bond between second and third carbon. Okay, whereas in this resonating structure, there is single bond between, okay, second and third carbon. How about the actual structure then? The actual structure contains bond which is in between single bond and double bond, and what do you call that bond as? Partial double bond. Any doubts? Partial double bond. Now, okay, in this resonating structure there is single bond between first and second carbon, there is double bond between first and second carbon. Therefore, the actual structure contains the bond which is in between single and double bond, and again it is nothing but a partial bond. Okay, so now here in this carbon carries negative charge, whereas in this resonating structure the third carbon carries the negative charge. Therefore, the actual structure carries partial negative charge on this carbon and the partial negative charge on this carbon. So this is going to be called as the actual structure. I hope it is clear. Yes, any doubts? Okay, so this is, what is this actual structure called as? These are called as resonance hybrids, isn't it? Resonance hybrid. Okay, this is the resonance hybrid of allyl carbocation. This is the resonance hybrid of allyl carbanion. Allyl carbanion. Understood? This is going to be the real structure and this will be the stable structure. Okay, yes.